Hello, good morning, good afternoon to everyone joining. First, for those that have been already watching the first part of the series, thank you for joining again. For everyone that's joining anew, this will be about time travel debugging using WinDbg or WinDbg. So first and foremost, introducing myself. My name is Kevin Ott. I'm a principal red teamer at Enviso Ares, so doing mostly red teaming, Tiber engagements, purple teaming, and all that stuff, but also doing some R&D, research and development, helping build our own implants and C2, and therefore trying to or being really familiar with debugging and the process of it. I'm also an instructor for SUNS 670. So that's the class on how to build your own implant from scratch and how to build red team tooling from scratch in C and C++. And that's also a bit of the scope of what we'll be looking at today. So for the debugging that we're doing, we're mostly focusing on programs that have been written in C, C++. We're not looking at programs that are being written or that are written in C# or similar high-level languages. So the program that we're going to be using is WinDbg. And for everyone that wants to follow the steps or the debugging steps that I'm doing, you can do so. I've published the code for all the different solutions in C++ that I'll be using throughout this webinar on my GitHub. And so if you want, you can pick this up. So github.com/shellhunter/sans TTD workshop. So if you want to pick that up, feel free to do so. Okay, so for those that have already joined the previous webinar, I think most of you should be familiar with how you normally do debugging. So you normally would just open your executable, and I'm taking Notepad now as an example, but could be anything, could be an implant that you've written, could be a loader that you've written, or any other program for that matter as well. And you normally open it up in WinDbg. You're used to setting breakpoints on certain functions using the BP command. And then you would normally go ahead and just run it, hit your breakpoint, and you start stepping into the functions that you want to look at. And suddenly you make a mistake and you step one step too far. So the interesting tidbit that you wanted to look at is suddenly in the past. And there's no way how to inspect the register or a return value of a function anymore because you stepped over it. So you have to restart your program. And if we're looking at rather small proof of concepts, that's not a big issue. That just takes a few seconds and you're up again and you can try again. But if we're looking at long-running programs or we want to debug a session of our implant that's running in process somewhere, and then we have to get set up all the way again and we lose some precious time. So that is exactly the reason why I'm a really big fan of time travel debugging, because in comparison to normal debugging, with time travel debugging, we are now able to step back in time. So instead of just going forward in a linear fashion, like in the normal debugging session, with time travel debugging, we're now able to step back into our code. And just to give a quick demonstration of how powerful time travel debugging is, I first want to step or take my basic OS info code as an example. So we're, in this case, we're looking at code that we have written, but of course, everything that can be, or that everything that you see here can be also applied to processes where you do not have the code. So for example, if you're into exploit development, and you want to see, okay, I want to debug everything, want to make sure that I have a crash, and then with time travel debugging, you can go backwards from the crash. We're going to see an example of something similar as the last example, but for now, we're going to get started. We do have the code at hand, so it's nice because we now can also check to see, okay, this is what it looks like in a debugger, and this is what it looks like with the code. So the code for this one is relatively simple. We're starting with a call to get native system info, and this will give us the system info structure, and we'll populate it with some information about, for example, the application addresses, so the minimum memory address and the maximum memory address that can be used by the program. We can look at the page size, and if you have been following the last webinar, where John was probably also talking about page size, although it's quite normal, or although the page size is normally set to hex 1000, so 4096 bytes, using this method, we can query it and just make sure that the page size is actually what we expect it to be. We can look at things like allocation granularity. So just a simple program to get some information about our local system. And then in a second call, we're going to use RTL get version, so a more or less undocumented function from NTDLL. And we're going to use that to get information about the major version, minor version, and build number. So I already went ahead and built this, but if you're just pulling down the code from GitHub, you just switch to release up here. You build the program, and then once the program has been built, we're now able to use WinDbg with time travel debugging to take a look at what's actually happening under the hood of this program. So to get started with time travel debugging, and those that have used WinDbg before, you're probably familiar with just clicking this button here, opening your tool, and then let it run. If you have already debugged something that requires command line arguments, for example, then you probably also know the launch executable advanced function. This is where we would need to go to actually start a time travel debugging session. So we're selecting our process that we want to start. In this case, we want to go to the workshop file, so basic OS info, 64-bit release, and then select our program. Okay. The program doesn't take any arguments, so we can leave those empty. And then the most important part of starting a time travel debugging session is to check this little box, and it will get started. And this will basically cause WinDbg, as soon as you launch the process, to record every CPU instruction and every memory interaction that the process does. And once you exit the process or you actively stop the recording, then you will have a file, and I'm going to show you that in a second, that will contain everything that happened from the start of the process all the way until the process has exited. So here we can also select a save location. In this case, I'm just create a folder on my desktop. So with the TTD recordings, we can then select this, and the file will then be automatically saved to this location. So hitting the record button we can see that it quickly popped up the window, the shell window from the process being created, the output being displayed. And if we just go to the workshop files, info, just because it was really quick, and we run it from this location, we can see that it gives us 4 processors. The page size is 4096. Processor type, so we're on x86 64-bit, and then the OS version is Windows 11. So program works as expected. So now let's take a look at what we can do with time travel debugging. So in a normal debugging session, and unfortunately, even though most of the time it works, sometimes it doesn't. And the reason why it did not work, or why you can see that it did not work, is it's missing the timeline view. So that should be an easy fix by just closing the debugger and then manually opening the run file. So these are the three files that are being created every time you create a time travel debugging session. The run file, that is the file that you can then open in WinDbg again to step through everything. And the IDX, the index file, that's basically the file that helps WinDbg to keep track of everything that happens. So function calls, memory access, and so on. So let's open this one. And even though WinDbg does not have the preview suffix anymore, in my experience, sometimes, especially when using time travel debugging, it happens that even normally this view should be opened after the process has exited. Sometimes it doesn't happen. So then you just open the run file manually, and now you're in the proper time travel debugging session. So what we can see here, what's different to a normal session of WinDbg is we now have a timeline down here. We're going to look at how we use that in a second. Then what we also see is we have a few new commands. And that's what I want to talk about first, because these commands are normally not available in a normal WinDbg session. So in a normal session, we do have step out to step out of a function call. We do have step into to follow the execution flow of a function. And we have step over if we want to treat a function call as a single step and basically just skip the function call. In addition to those commands that we usually have, we now also have step out back, step into back, and step over back. So normally, if we are in our debugging session and we use, for example, the trace command to single step, we would just step. So now, in this case, I now stepped into LDRP initialize. And if I wanted to know what the parameters for this function call are, and I would have stepped a few more times, I wouldn't be able to go to recover those arguments because it might have already been tampered with or modified by the flow of execution. With time travel debugging, we can now revert the instructions that we just stepped by using the T minus. So we can see that we went from this move command to the push, and then now with the T minus, we're back at the previous instruction. Using the R for registers, we could then inspect what the registers look like at this specific case. So now, instead of just stepping linearly and progressing through our program, we can revert the instructions and go back in time inside of WinDbg. The same goes for the go command. So normally, if you don't have a breakpoint and you just hit go, the process will continue. And if you accidentally hit go, then like in this case, you'll somehow end up in anti-terminate process. So the process is actually done, and now you would have to restart your process to do the same debugging again because you stepped a bit too quick or you forgot to set a breakpoint. With time travel debugging, we can do the same thing, but if we also append a minus to the G command, to the go command, and hit that one, we're actually able to go back, and now we're at the beginning of our debugging session again. So we can see here LDR initialize thunk is the first function call that's recorded in our time travel debugging session. So every time we want to go back to the start, we can use that function to basically go back all the way. In a time travel debugging session, we can still set breakpoints like we normally do. For example, our get native system info call, get native system info. And we can see here it's part of the kernel base DLL. So we can take our call, we can set a breakpoint, and we can go just as we would in a normal debugging session and hit our breakpoint with this command. We can also, if we now go and like, oh, I still wanted to check something with the function call, and now I have to restart my program. But now we don't have to, because if we use go minus again, we would again go back to the breakpoint. So we can hit the breakpoint both if we're stepping forward and if we are stepping backward or completely going backward through our time travel debugging session. So that's one of the most important features of actually using time travel debugging. So the last one, step. So if we step, for example, and this is the cool part, because now we're inside of get native system info. But what if we want to inspect what happened before that function call occurred? We can now do this. And for example, by using the P, so by step and then minus, because we're now in the function prologue of get native system info, if we now step back one step in the execution, we will end up in the function call or in the piece of code where get native system info was being called from. And if we do that, we see now, okay, now we're in kernel 32 get native system info stub. So from there, we could even go back even further. So we can trace back our execution. And if we do that once again, what you'll see is we'll end up in the code that we have written. So we went from a Windows API that was called and could go back to our code. Now, because this is code that we have written and we have access to, for example, to the PDB file, WinDbg enables us to also go back to our code. One important piece that is now that has now changed in comparison to before is you can see here that it went from assembly mode to source mode. So where before the P and the T instructions only put us forward one instruction in assembly, now it will put us forward one line in code. So if we do step now, we can see that we hit our breakpoint. So if we step again, or if we put a breakpoint, and that's the cool part, we can now put breakpoints in our code just as we would be able to in a debugger inside of Visual Studio. Oops. So if we now continue our execution, we would see that we get back all the way, step out. And now we're basically inside of our code and we're able to step over these functions and we could just follow the execution of our program in code. So especially if you're writing loaders or C2s, most of the time, just stepping over code is not the granularity of debugging that we want to have. So what I mostly go back to is by clicking the assembly here, you can then start stepping over assembly instructions again, instead of just stepping over individual lines in the code itself. So let's step out of these functions again. So now we're here. Okay, so to summarize, we have three new commands. The step out back, step into back, and step over back. And then if we go from the GUI, and then we also have the T minus for taking a single step back, the P minus for stepping back, and then also G minus for returning to the beginning of our function. The next part that we have, in addition to the normal features of WinDbg in time travel debugging, is a time travel debugging object. So let's jump back all the way to the top. Okay, and hit the breakpoint. So we'll close this one for now. Okay, so now we're at the beginning of our session again, just to make sure that we can go from there. So and again, for those that have been following the first session of, or the first session of the WinDbg series, you've probably seen the dx command. So this is a command that's relatively new, that's exclusive to WinDbg Preview, and you can use it to evaluate an expression. So we do have a pseudo register that's called current session. So current session, this is our current debugging session, and this object basically holds a lot of information that we can access using the dx command. And you can already see that the first one, this is our processes. So in this case, because our current session, we only debug a single process, what we will see is also that there is only a single process being debugged. So we have our process ID here. And if we take that process ID, because normally there can be also multiple processes, especially if you're in kernel debugging, there would be multiple processes. So it's an array that's indexed by the process ID. And if we look at the individual member of that process array, we can see that for each process, we have information about the process handle, our name, so what the executable is. Here we have our process ID again. And then we also have information about the threads, the modules, environment variables, and the process environment block that contains a lot of information about the running process that you could, for example, also access with the extension bang PEB. So this just gives us a lot of information about the currently running process. And this could also be accessed from the current session processes array. Then we do have attributes, devices. So most of these are not really that interesting, but the current session has a second object that is quite a lot more interesting. And that is the TTD object. So if we use dx command to evaluate that expression and take a look at the TTD command, we can see that it has a few methods. For example, it has a method called calls, and that one takes the function name or takes a function name as parameter that you can then use to inspect that function call. And that's one of the powerful things of time travel debugging, because the execution of our process has already ended. We can ask WinDbg about any function, how often it was called, at which point in our debugging session it was called, what its function parameters were, and what the function returned. And we're going to take a look in how to use this in a second, but we also do have the memory. So in addition to looking at what functions were called at what point in time during the execution of our program, we can also look into the memory and when what piece of memory was accessed. So we can basically provide a memory range or a range of memory addresses and then basically inspect every occurrence in our execution when that specific piece of memory was accessed. So that's really powerful, and that's something that you cannot do with a normal debugging session. You need to have a time travel debugging session for this. So as we saw in the code, we used two different API calls. So let's take a look at those. So dx for the expression. Then we have our @ sign and the $sign, current session, .ttd, .calls. And if we just do it like this, we will get the same information that we got before. So if we go back in our code, we can see the first one is get native system info. So let's attempt to look at all calls to, and let's do asterisk. So we want to see all calls to that method in any module. And then we hit another asterisk here because in kernel 32, the method is called get native system info stub. So using this one, we might be able to get all of those. And you have to put them in quotes. Keep forgetting that. There we go. Okay, So now we see two different calls to to get native system info, and the second one is probably get native system info stub. The problem is we only see two in the array indexes here, and that's not really helpful. So what you can do is, and that's basically like in most program languages, so you can use the angle brackets to dereference that array. And now we're able to look at what kind of method was actually called, because we see that the first method, so index 0, that's being called is kernel32 get native system info stub. If we look at the second call, so at index 1, we can now see that it calls get native system info. That is because most functions that are implemented in kernel32 are just stubs that will then call into the kernel-based DLL where the actual method will be called. So now that's really cool already. We can even get a timestamp of when this execution occurred. We can see that the return value was 0, so preferably, that means that this one was successful. And we can also take a look at the parameters. Now, WinDbg is not particularly smart about handling parameters. So because it doesn't know what the actual function call getNativeSystemInfo looks like, it will just give you the first 4 parameters that in 64-bit are passed in the registers. And if we go back to our code, we can see that getNativeSystemInfo doesn't really take 4 parameters, it only takes 1. Still, WinDbg will give us all 4 parameters. Now, if we take a look at this call, we're now just inspecting what this call looked like. What we can also do is we can now time travel to the exact moment when this call happened. So in this case, we can both time travel, and here are 2 links that you could just use to basically time travel exactly to the moment when both the function was called and just before the function returns. We can also do that manually by using the time start member, and that member object has a seek_to function. So using that function, we are now traveling to the exact instruction where our call occurred. And if we now unassemble, we would see that we are indeed at the exact instruction where a get native system info stub was called, and we can see that it is a jump to the import address table where we would basically then import to where the import from kernel base is referenced, and then this would take us to kernel base itself. So if we follow or if we step, we are exactly where we want to be. So now we are in kernel base get native system info. And this is how we can then go from call to call in our DLL, in our program, in our execution, and expect exactly what was happening during these calls. Now, looking at our calls like this it's pretty cool, but visualizing when these calls occurred and how it looks like on a timeline is even better. So, and that's exactly what the timeline in WinDbg is for. So here, we can add different things to our timeline, and we can add exceptions. So every time our program through an exception, we can put that on our timeline. This one's automatically added, so there is no exceptions. But if there were, you would see them immediately on the timeline. We can also put breakpoints on our timeline. So if we do have 2 different ones. So let's take these 2 breakpoints and let's add them to our timeline. So selecting breakpoints, and then let's take get native system info. It will take a while, and then we'll see that it did add our breakpoint to the timeline. Excuse me. So So that's pretty cool. We can add multiple breakpoints to our program and then add them to the timeline to make sure that we see exactly when in the execution these breakpoints would be hit. We can also add function calls to our timeline. So let's take kernel base, and it also wants to have both the module name and the function name itself. So kernel base exclamation mark, and then get native system info. And now we can see that our breakpoint also lines up exactly with the start of our function, but we can also go to the end. And you'll see that once you issue these commands, I don't want this one. Once you click on one of the two arrows, it will take you to the exact moment in time before that function call returned using the same command that we used previously. So by clicking on these little icons, WinDbg in the background will just issue these commands. So we could technically use these commands, but having everything visualized on the timeline is, in my opinion, a bit nicer way to work with function calls in time travel debugging session. Okay, so let's do the same thing for our second function call, which would be ntdll rtl get version. Okay, and so we see that in addition to our call to get native system info, we now also see RTL get version. If we hold down the control key and then use the scroll wheel, we can also zoom in on our function calls, and we would be able to easier differentiate between the start and the end. But as RTL get version is a pretty fast call, there's almost no way to basically get those two separated. So even if you scroll in all the way, they won't be really separated. But if we take our function call for, oops, for get native system info, we can see that this function call takes a bit more computing time. And so it's easy to zoom in and then have the start and the end quite apart from each other. So it's easier to navigate between the two in this case. So if we look at the function call again, one thing that we can see is also that it's quite easy to determine, the actual return value. So it's very easy to look at the individual values. Now, looking at just a function call is already pretty cool, but what I want to show also, it's easy to then drill down on the layers of calls that you have in Windows. So when we have our call from kernel 32 to kernel base, the next step is that it will go to ntdll and call an undocumented function. And that undocumented function is ntdll nt query system information. So, and we can now inspect how this function call, how these series of function call would look like by basically first removing this one, because that's what we don't need anymore right now. And then if we go ahead and add two calls, so first kernel 32, we get native system info stub. Okay, and then we add another call to ntdll nt query system information. And what we can now see is, and I hope it's visible halfway in the, or it's decently visible in the screencast. But what we see is that the first function, and let's make it so we start with kernel 32 DLL, then the next call will go to, and we can zoom in a bit right here. So the next call will then go to get native system info from where a call to NTDLL query system information will be issued. And if we zoom out, we can also see that this call is basically then issued twice. So here, and that's very difficult to distinguish because the calls are so close to each other that the two little icons do overlap. But basically, the NTDLL NT-query system information call is done twice in quick succession. And then once that call finishes, that's basically because it's inside of the two little angle or inside the two little arrows of get native system stub. We know that this is a function call that's issued by get native system info. Now, why is this one issued twice? And that's also now something that we can explore using time travel debugging, because when we go to the end, and it's a lot easier to use the seek2 command. So I'm just copying the one from that WinDbg gives me. And then I'm just swapping out time start with time end. And now I'm basically at the end of that specific function call. And if I now inspect the RAX register, which is the CPU register where function call or function return values will be stored, we can see that this one is successful. That shouldn't be. Let me quickly check. Okay, that's interesting. So this one was actually successful. So if we look at let's look at the second one and see why that was. So this one is successful as well. And if we inspect the parameters of both calls, we can see that it will use the system information class. So this is what the function looks like. So you will pass the system information class, then a buffer to receive the results, and the length of the buffer where the results will be received. And it will also take a pointer, and that will be populated with the actual size of the system information buffer that was populated by the function call. If we look at the first one, this one is an enumeration that has several values. So you can use the anti-query system information to query all sorts of different information. And in case of get native system info, it will use the enumeration value of 0, which corresponds to system basic information. So going back to WinDbg, you can see here that this is in the system basic information. And then the second call is then, instead of system basic information, it will then issue a call to system processor information. And that makes sense because if we go back to the code, we can see that among the information that we get is we get the W number of processors, and we also get things like the page size, which is probably part of the system basic information. So this function basically calls the underlying function twice to get different parts of information from the operating system itself. Okay, jumping back to WinDbg, looking at the time really quick. Okay, and so these are the methods that you can use to jump back and forth through WinDbg. So I want to show one more use case for WinDbg and time travel debugging. And I'm going to open another solution here. So let's go here. So one use case that I'm a big fan of when looking at time travel debugging is actually shellcode injection. Because with time travel debugging, you can now debug the injected process and debug the shellcode of that process to make sure that everything is as you would expect it to be, and you can step back and forth through the shellcode, which is really nice to do. So as an example, I have here a version of threadless injection written in C++, based on the code from CCOB that he wrote in C#, and just converted it to C++ basically. So what it does is it has a shellcode loader stub that will be responsible for actually jumping to the shellcode. Just to make it a bit more, or to simplify it, I didn't use any real shellcode, but just a knob instruction and a break instruction. And then the logic of this process is that it will override the function stub of kernel base exit process with a jump to our shellcode loader, which will then have the shellcode itself pre-pended. And then this will set up everything needed for our shellcode and then last jump to the shellcode. If you are interested in how this technique works in particular, there's the talk from CCOB at B-Sides Simru, and I think I just mispronounced it horribly, where he talks exactly about how that specific technique works. If you haven't seen it, I can definitely recommend checking out that talk. But now in the context of time travel debugging, what we want to make sure is that this shellcode loader, or stub, is working just as we expect it to. So before, we just went ahead and started a process under time travel debugging. And why this use case is so interesting is because it takes the second variant of how to time travel debug a process, and that is by attaching. Because to time travel debug, you don't have to start the process in a time travel debugging session. But as you can see here, it already says that attaching to a process supports time travel debugging itself. So we can select our process notepad.exe, and then also we do have down here our record with time travel debugging checkbox. So now by selecting that process and checking that checkbox and hitting record, it will also record our time travel debugging session. So now we can run our tool, our injection. Plus inject. Just need to get the process ID of Notepad 17372. So 17372. It will do the injection. And now because it does hook exit process, once I close my Notepad process, it will basically run my shellcode. So let's hope that this time the time travel debugging is set up correctly and I don't have to start again. And because Notepad is quite a large process, it takes a bit until it's fully processed. But here we can now see that this is what it should look like. And as I already mentioned in the beginning, that now that we have an exception, so because the last instruction of the shellcode is just a CC, as soon as it tries to continue and tries to step over that breakpoint, which it will do automatically, it will run into an exception because the next piece of memory is not accessible, because it's not a proper shellcode that tries to repair the stack and everything. So that's why in the end it will fail. And it's also nice because we can now see the exception. This is where time travel debugging can come in really handy, because we now can jump to that exception, and from that exception, we can basically step backwards in our code, and we now see that if we unassemble, we are in our break instruction, and technically we can now step back all the way through our shellcode. So it means if this was an exception in our shellcode or a access violation, for example, in our shellcode, we would now be able to step back from the point of the exception where it occurred back in our shellcode to determine exactly where in our shellcode that specific that specific exception was caused from. So what was what were the instructions that were executed before before the program failed? So that is really nice. Now let's jump back to the exception, because another really nice mechanism that you have in time travel debugging is you can actually determine when a certain register was last modified. Let's take this here as an example. So we see that our crash occurs because we are trying to dereference RAX, which leads to an exception. So what we can do now is we want to figure out where was RAX actually set. So where does the address in RAX come from to make or to determine if we can change the behavior to make sure that it's properly set. There is an extension command called TT for time travel, and that supports the break on register. So BR, TT, BR, and then minus because we want to search backwards. So this one allows us to break every time a register is being accessed. So TT, time travel, break on register, minus to search backwards, and then we provide RAX. Give it a go. And we can see here that one of the last accesses was move and then this value into EAX. Interesting, that's not really the one. Okay, let's try this again. Interesting. So here the demo god is not with me, because if we take the output from our command, it does create a allocation at this specific address. So if we unassemble here, we can see that we do have a pop RAX here and then sub RAX5. So normally when this command is issued from our breakpoint, it should hit this sub RAX. But what we can do is, because this is an exception, we can just step back one time. And if we issue that command now, we should hopefully get the result that we were looking for. Okay, so apparently something in the recording went wrong. So it doesn't hit the exact spot where RX was set before this in3 this in3 instruction was called. And yeah, even though WinDbg did not lose or did lose its preview, it can sometimes be a bit finicky. What helps in this case is just to redo the recording, the time travel recording, and then sometimes that fixes the issue magically. But in this case, in our shellcode, one thing that we can also do is if we want to go back to the exact moment in our recording when that specific shellcode was executed, we do have a few options. Option number one is we could set a breakpoint to that location. So BP, put a breakpoint here, and then we go minus. So we go all the way back, but it will hit the breakpoint just as it would hit during a normal debugging session when we go forward. So let's go to the crash again. The second option that we have is to also use the TT command. So bang TT, and then BR minus search back. This time we're looking at the instruction pointer, and the command takes another parameter, which is an address or a value. In case of RIP, the value is an address. We could put any value here that a register. So it will basically search back until the specified register is changed to that specific value. That means that when our instruction pointer becomes the address of our shellcode, that's when we want to stop. So if we search back, okay, that seems to be broken. Sorry, I can't really show it right now. It definitely worked when I was testing out the demos. But technically, you could use that specific command to search back when the instruction pointer hits a certain value, and that's how you can then jump to the actual buffer that you have allocated in a remote process to then step through. And if we go minus, we could now step through the instructions of our shellcode and basically inspect and make sure that everything is set up properly. For example, that the addresses that we hard-coded are properly determined, and that once everything is set up, that it then successfully goes uh, to our actual shellcode and runs our actual shellcode just as we expect it to be. And it just saves a lot of time if you do this using time travel debugging instead of just trying to restart your shellcode loader every time. So yeah, and with time nearly nearing the full hour, that was a introduction to time travel debugging. So to summarize, with time travel debugging, we can record a full execution of a program, or we can attach to an already running program and can record a subset of the execution of that specific process. And then once we have recorded our session, we can then step backwards and forwards in time in our debugging session to determine the root cause of a crash or to inspect the inner workings of some of the API calls that we're issuing to determine what exactly is happening, what's going on when we do issue a specific call, and to dive deeper into what happens internally with some of those Windows API calls. Now, in 670, we do use time travel quite extensively to debrief some of the labs and do exactly what I just did with the basic OS information. So a deep dive into how these Windows API calls work internally. And if that is something that is interesting for you, and not only looking into how these works, but also to create these tools from scratch, then I would definitely recommend taking 670. The next runs will be in Baltimore in June, and then in July in Amsterdam. Both of those will be with Jonathan Reiter, the author of the class. So if you want to take a peek into developing your own implants and get started and don't know where to start, that class is really awesome for that. So that was it from my side. Thanks everyone for listening, and that would be all for today. Thanks.